This is the video lecture for the Design Failure Mode Effects Analysis for ME 415 and Engineering 466. The benefit of doing a Design FMEA, or we'll call it Dfmea for the rest of the lecture, is to, as indicates, identify failure modes, also to estimate the risk of those failures to our product or process, to prioritize the actions that we will take to reduce or eliminate that risk, and then build a design test plan or a manufacturing control plan. The primary directive here is we want to eliminate or reduce the risk of failure by proactively improving reliability, customer satisfaction, and safety. Some food for thought here. Douglas Adams, the author to Hitchhiker's Guide to the Galaxy, said the problem with designing something completely foolproof is to underestimate the ingenuity of the user. Great example of this is a lawnmower. I think we've all seen the warning signs on a lawnmower to not pick up while running. This is due to somebody thinking that they could trim their hedge with a lawnmower running and then resulted in injury to their hands. Since you cannot eliminate that from the design of a lawnmower, then engineers were forced to put warning labels on the mower deck telling people not to pick this up or they will suffer injury. So there's our options as a design engineer. We can either eliminate the cause for injury or warn against it. Our preference, of course, is to eliminate. And this is why we do design FMEAs, to help us anticipate these problems and get them designed out of our product. So where does risk come from? Besides the obvious potential safety hazards we just talked about, they can come from any of these other areas that we've shown here, such as poor control plans or standard operating procedures on the factory floor, or process capability, or issues with material coming in, or poor specification limits set for the product and the manufacturing. Then we also have measurement variations, online or quality control, and machine reliability or vague workmanship standards. But risk can also come from unclear customer expectations of the product or unclear user habits that could occur. Either way, they all come to cumulative risks that we have to deal with as an engineer. So how should you go about mitigating risk? Well, you first have to start with these questions in mind. What can go wrong with the design, the product, or the process? How likely is it to happen? And what are the consequences of it happening? That is, once the failure has occurred, what's going to happen to the user or the product? Key thing to remember here, risk of uncertainty is your responsibility as an engineer. You have to design it out of your product. Types of FMEAs that you're going to see handled out there are as shown here, though the two that we are going to talk about most here today in this lecture are going to be the design FMEA and the process FMEA. Both of those are going to analyze either a product or a process, trying to understand how could either a failure impact the product function, or how do process inputs and outputs occur such that we want to eliminate error and improve efficiency in the manufacturing process. So when do we start a FMEA? Well, in doing Dfmea or Dfmea, the design of a product, we're generally going to start once we've selected a concept and we're moving forward with a design. Then as we move through the project, we'll improve, and when we get to tooling and pilot runs, we'll take the data that we get from our product testing in pilot and complete our FMEA. However, as the product is in what we call the commercialization stage, that is, it's in production, product is being sold out to the field, we're going to continually update the FMEA based on information we get back from warranty data in the field. On the manufacturing side with the process FMEA, it starts at essentially the same time. Once engineering has selected the design and we're starting to take a look at it as to how it's going to be designed and manufactured, then manufacturing is going to start working on their process FMEA. And as we get into the tooling phase and with a pilot run, then we'll complete pilot production approval and fill out the FMEA and get our classification. However, The production FMEA, the process FMEA is never really done because as the product is in production, there will be continual updates to the production process to improve efficiency, reduce costs. Those will always have an impact on the process design. And so the process FMEA is never really quite done. That's why we refer to both of these as living documents, because they're continuously being improved and updated as we try to stay ahead of this thing called risk. So the roles of the Dfmea, first of all, it's going to be preemptive. It's going to allow us to anticipate failures before they occur. It's also going to allow us to prioritize our resources by taking a look at where our greatest risk exists and then applying our resources to mitigate that risk. It's also going to allow us to document any actions that we have taken by a team to mitigate risk. And because it is dynamic, the document is going to be regularly reviewed, amended, and updated. Key thing to bring to your attention here is that an engineer who is good at doing design FMEA is going to be a very critical asset to a company, because oftentimes companies can find themselves in court through litigation on product liability. And any company who can come in and show due diligence by having a completed design FMEA, showing that the company has taken every step possible to eliminate risk in the design, is going to be acquitted. They're going to be found innocent. So this is why we stress getting to learn how to do this, though you have to keep in mind design FMEAs don't occur overnight. They take time. So you got to get started early. You want to sit down and do them methodically, a little bit at a time, until you get everything covered in your design, looking at all risk areas. So to get started, a great place to start is start with your function tree and the functional analysis. Start with a system. Then once you've covered the main system performance criteria, then move into the subsystems and then into the subsystems and down to the components. Don't start at the component level. If you do, you're going to wind up with a lot of repetition, and FMEAs are too long enough as it is to not get into that area. So our recommendation, start at the system level and work your way down. Key thing we're wanting to figure out here is the failure modes. What could occur in the product or process that's going to create a perceptible problem that the user is going to notice? And when we look at that, we're looking at effects. So we want to understand, if not detected, either corrected or removed, will that failure then create an effect that is going to be perceived by the user? Also, we want to understand that the failure mode can also cause potential failure modes in higher level assemblies, and we can track this through the function tree. So we want to understand failure modes. The other thing you also want to understand is the effect, the impact of the item's functionality on the performance as perceived by the customer, or more specifically, the user of the product or process. Methods that we can use to find failure modes, though. We can take a look at past problem reports with associated similar products. We can also look at warranty data of similar products. A great source of that these days with the internet is to go look up blogs by customers on particular products. There's all sorts of blogs out there related to automotive warranty, consumer products warranty like washers, dryers, refrigerators, and such. So there's a lot of different information you can get out there. But you can also review your function block diagrams, your functional analysis work, your function trees, and understand by taking a look at the way you have your product design, what are the potential methods, and looking at inputs and outputs and the control parameters that you have in the design, how can they fail? All of this information can be pulled together to anticipate failure modes. Now, another thing to notice too is that failures can come to us in different fashions, and here's the three most classic that we see. The effect that a customer may see of a perceived failure in the product could be caused by one or more failure modes. Classic example, my lawnmower won't run. Well, the first failure mode could be I have a blocked gas line, would cause the failure of the mower not to run. Another failure could be that I have a failed ignition coil on my mower, so I have no spark. Now, you'll notice that I have the same effect, more won't run, but they're two different failure modes, two different root causes of failure that we have to track. It is also possible that a particular failure mode could cause two different effects on the product. Depending on the severity of the failure mode, could cause noise or could cause full loss of function. But both come down to the same failure mode, same root cause. Or it could be that in order to get a perceived failure on the product, I have to have two failure modes occur on a product before the customer will notice that they have a problem. Either way, each failure mode that is caused here is a line item in the design FMEA, and if you have more than one effect, then that failure mode is going to get listed twice for each effect with each root cause. So, cause. These are the sources of design process error, design weaknesses that are going to cause a failure mode to occur. And we want to make sure that we list every possible cause associated with each failure mode. And we also have to recognize that these causes that we put down have to be root causes for the failure. So some examples. If we have, say, loss of a function of a product, let's say we have a seal that won't seal anymore. Well, the cause of the failure could be that there was surface contamination, but that's not necessarily the root cause. The root cause may be incompatible raw materials, or maybe there's an insufficient plating specification. Or maybe the failure loss of seal was due to wear, but the root cause could have been inadequate lubrication at the seal site, or maybe it was inadequate hardness of the shaft surface involved with that. Either way, we got to track down what these root causes are. You can see here we have other examples for maybe something that got loosened, maybe it was due to inadequate torque specification or an insufficient torque retention feature. Classic example, use of a lock washer versus a locking nut or a nylock nut could be key areas where the failure could come from. Current leakage, maybe we had a low resistance short, maybe there was a poor insulation involved, fractured welds, maybe it was due to low strength welding material, maybe it was just an insufficient number of welds used for putting the product together. Once we've identified root causes, now we have to take a look at what design controls do we as engineers have. And it really comes down to two key areas, prevention or detection. And in prevention, as you can see here, these are the four key classical areas that we have to work with. We can do numerical analysis, that is math models. We can do fatigue analysis, FEA or classic analysis that we can do looking at stress in the product, kinematic analysis looking at force and motion, or also then again doing reliability analysis, taking a look at fatigue models in the product. The other side that we have to use is detection, that is testing, inspecting. Classic tests that we'll use as a design engineer is performance test, reliability and durability testing, or maybe what are called alpha and beta site testing. That's where we're going to take preliminary product or some prototypes. We're going to give it to a group of users, let them test it in the environment that we expect to see the product in, and they're going to collect data for us and provide that information back to us. That's classic alpha and beta site testing. But the important thing to understand here is which is more important to us as design engineers. Is it prevention or detection? Key thing you want to remember here is you want to prevent failure from occurring, so obviously it's prevention. Detection is things we can use when prevention cannot be applied. In doing a FMEA, we have to rank our risks. So we're going to create what's called an RPN, or risk priority number, and we're going to look at three key areas in order to generate that risk priority number. We're going to take a look at the severity of the failure effect on the customer, and we're going to rank that from a 1 to a 10 depending on how severe it is. Higher numbers, of course, being worse. We're going to take a look at the occurrence, the frequency at which the failures could occur. Again, not likely is going to be 1, severe is going to be a 10. And last, we're going to look at our ability to detect or control this failure from occurring. And again, if it's likely If we're likely to catch it early, which is good for us, that's going to have a low number of 1. If we're not going to have a good ability to detect it, then that's going to be a 10. So our range of RPN numbers here using this 1 to 10 scale with the 3 items we're tracking is going to be 1 to 1,000. And the key question I get asked all the time is what level of number would cause us to definitely want to look at the problem. And in general, that number would be about 120. So anytime you're over 100, you definitely want to take a look at it. But I would also say that if you have anything that has a severity ranking of 10, you definitely have to look at that too, and maybe even some 9s. And I'll get into that in just a little bit. So again, we want to create a risk priority number. We're going to do that by taking the rankings that we have for severity, for occurrence, and for detection, and multiplying those together to get our risk priority number. So here we have a rating scale showing the 3 areas: severity, occurrence, detection, and the ranking scales from 10 to 1. Now, I'm going to focus mainly here on the severity because that's the most important area that we need to look at ranking-wise. And the reason for that is generally when we look at the design of a product, unless we significantly change a function or eliminate a function out of the product, the severity of the effect of the failure of that function is never going to change. So that's why we're focused on this so heavily. Occurrences we can have an impact on, our ability to detect we can have an impact on, but severity, again, unless we can eliminate the function out of the product, that's probably not going to change. So what creates a 10? Well, as it says here, if it's hazardous without warning and it creates a personal safety issue, that somebody's going to be grievously injured or killed, that's a 10. We're going to rank it as such. If we have a failure that's going to be hazardous with warning but could cause property damage but no extreme safety issues, then we're going to rank that a 9. And if the product's going to lose its primary function and be totally useless to the customer, that's going to be an 8. From there on down, the rankings don't get as critical. Those top 3 are very important though. Reason for that is today in the corporate environment, companies don't like to see 10s in their design FMEAs, and oftentimes when design FMEAs have 10s in them, they're going to be reviewed by the safety committee and the CEO is going to sign off of it. So you're going to find as an engineer, you're probably going to get a lot of pressure about eliminating 10s out of your product. But it can't always happen. Sometimes you're going to have some 10s in there, so you have to be able to show due diligence as if you do have a 10, what are you doing to mitigate the occurrence and improve your ability to attack any root cause that would allow that failure to occur so you can get that hazard out of the product. So again, as stated, severity rankings, 10 is potentially catastrophic, lethal without warning. 9 is injurious but not life-threatening, or it could have a major loss of property. And 8 is extreme customer dissatisfaction, complete loss of the function of the product. So let's start with the design FMEA procedure. The first thing we want to do is we want to look at our function tree or our functional analysis, and we want to look at our systems involved. And so we want to put down what is the function of our device, as we can see in the first column. Then we're going to list our subsystem that we're ranking here and what that function is. And then we're going to start asking ourselves, how can that particular subsystem or part function go wrong? In the case here, we're looking at a charging system that may be foot pedal operated. It has a gear train in it that's going to run a generator, and we're going to use that for charging batteries. So in looking at the input system, maybe one of our first failures, obviously it wouldn't oscillate, wouldn't allow us to pedal the system. Or it could be that we have a problem when we're pedaling the system, our foot may slip off. So here's 2 potential failure modes. So from that, we're going to then determine next what the effect is on the customer. Also, we look at the gear train, maybe another failure mode we have that it won't rotate. It won't allow us to take the pedal action and get it to turn the generator. If we take a look at the impact on the customer, we'll see that for the first one, they can't operate the system. That's obviously going to be an issue. Or with the second one, foot slips off the pedal, they can't operate the system comfortably. They might still be able to do it, but the operation is going to be interrupted by this discomfort of having to put your foot back on the pedal. Or with the third item, again, like the first item, can't operate the system, product becomes useless. So now we have to go in, once we've identified these effects on the customer with a product, we got to identify the root cause. Maybe in this case, we're looking at a bearing failure overstress or a shaft bending due to overstress. Or it could be, in the case of the pedals, the foot slipping off, that maybe the friction material using is just too low of a coefficient of friction with foot, and so the foot wants to slip off. Or with the case of the gear train not wanting to rotate, maybe it was due to a gear failure, again due to force overload. So now we have to ask ourselves, what design controls can we apply here? Maybe the engineer came in and said, well, for the first one, we'll go ahead and do a life test. For the second one, we'll do some design analysis. For the foot pedal, we're going to do some material testing, see if we can find a better material that has a higher coefficient of friction. And for the gear train, maybe we do both a design analysis and do some life testing to confirm that the system is okay. Once we have these things figured out, now we can go in, we can rank what our risk is. So here we see an example where we've put some stuff together and we've said, okay, with the charging system, looking at there's no voltage getting to the battery, we've lost function, so we can't charge the battery. And we say that it's due to an loss of function at the input system. That has a severity of 8. We take a look at what the currents level is. Well, it might be a moderate currents, so that's been ranked as a 5. And the engineer said our ability to detect is going to be at a level 3 because we could test and do some design analysis on there. So that gives us an RPN of 120. And so on down, if you look through the rest of the rankings, we're looking at bearing failure, overstress, or shaft bending overstress. We've got life testing and design analysis. Again, 5s and 3s. You'll notice that in all of those that are involved there where the system can't operate due to loss of function, those are ranked as 8s. And when we get down to the foot pedal slips, or the foot slips off the pedal, we can't operate the system comfortably. Well, we still have the primary function of the product, but it's not operating well. So that's not as severe. We got it ranked as a 5. Occurrence level, again, is ranked here at a 5. And our detection level with doing material testing, we got set it as 3, so we get an RPN of 75, and so forth. So we put this all together. The next step we're going to do with our design FMEA is we have to then determine the actions that we're going to take to reduce these RPNs. So in the case of some of these high rankings here, we pulled them together. We're going to say that for the input system, we're going to run a full analysis. We're going to look at stress. We're going to look at friction, we're going to look at wear, and we're going to address those issues for the bearings and the shafts. We're going to set somebody to track that. In this case, we've got an engineer by the name of Mr. Heisey who's going to go in and rank that or track that. That doesn't necessarily mean that Mr. Heisey is going to do all the work, but he's going to be responsible for making sure that the work gets done. Once you've had it done and you've completed your actions, then you can go in and re-rank it. In this case, as you can see, we haven't eliminated the impact of the failure on the product or reduced it in any way. But what we have had an impact on due to our analysis and testing is on the occurrence and our ability to detect. And so we've got acceptably lower risk priority numbers. And that's the whole idea behind the FMEA, is to put together for ourselves, as shown here, a list of recommended actions, our ability to document what actions we took, and what impact they had on improving the performance of the product and mitigating the risk. Some strategies to apply when doing a FMEA. Well, you always want to start with your known safety issues first. From there, then you want to focus on your high priority design requirements in your product, going through the various systems, and you can find these either through the QFD, that is the House of Quality, through the priority ranking there, or from your decision matrix tools as to which items were ranked as being most important versus those other features that were less important. Once you have those determined, as you're going through the failure